again, time for another little bit of particular chemistry that someone asked for. It's about PPM, parts per million. Not specifically about how to calculate it, but we'll do that anyway. But also the conversion between parts per million and a couple of other things. So first of all, parts per million, PPM. There's a second one there. PPMV. It's kind of a subtle difference between parts per million and parts per million volume, which is what the V stands for. Parts per million is all about grams. So parts per million volume could be about any volume unit, but for a chemist, cubic centimetres is usually the way forward. So parts per million volume, ooh, that's not a good V. There we are, parts per million volume against parts per million, which is supposedly parts per million mass, but we just call it parts per million. What is parts per million? It is just a ratio unit. Unlike concentration in the true sense of chemistry, which is moles per cubic decimetre, parts per million is a ratio where you divided the same thing by the same thing in terms of units, so the units cancel out. Hence it's also termed a pseudo unit, meaning it's not a real unit. Real units are SI units and use SI, all the basics of SI, standard international units. Pseudo unit because it's not one of the SI units. Doesn't stop it being used. You know, it's the same sort of thing as people still talk about pounds of stuff in weight, when in reality that's not correct. Weight is obviously a force. So when you talk about what we're doing today, PPM, and particularly I was asked about moles per cubic decimetre. Parts per million will always be parts per million will be bigger than the moles per cubic decimetre. So why would you bother to do it? Well, when moles per cubic decimetre gets down to really small quantities like 0.00072, it looks quite ungainly. But when you do the parts per million version of that, it will be a much bigger number, which means all the decimal point 0.000 thing will go, and it becomes a more manageable in terms of your handling of the number as a number in your head. So parts per million, concentration, and also percentage as well is they're all interchangeable when you do the right things. So I'm going to clean the board and we're going to come back after the edit and do a little bit of first of all parts per million, and then we'll do some conversions. I'll see you in a moment. So some little bits and pieces about the parts per million idea. Probably worth making some notes if you're really unsure. 1 part per million. What that would mean is 1 gram in 1 million grams. Seems like an awful lot of grams. Well, it is. Useful to be able to interchange these here. So there are 1,000 grams in a kilogram and there are 1,000 kilograms in a tonne. So therefore 1 million grams is 1 tonne. So 1,000 kilograms or 1 million grams. So you need to be able to interchange those. Hopefully you can. So when you look at something that says, oh, it's 240, only a number, it'll be a number, 245 parts per million. This is an example of sulfur dioxide in the air. What does that actually mean? It means, well, 245 better. 245 SO2 particles, molecules, against 1 million, which is 10 to the 6, of the particles that make up the air. I'm having terrible trouble writing. So 245 SO2s in 1 million particles of air. Now of course air is not one particular substance, it's a mixture, but that's the concept. So 245 particles of SO2 in 10 to the 6 particles of air. But you don't really think of it like that. What you really do is you go, oh well, we need to do this. We'll come to that in just a second. When you do parts per million volume, it's 1 centimetre cubed in 1 million centimetre cubed. So in a similar thing to that, that is a cubic metre. So it's 1 centimetre cubed in a cubic metre, which is quite big. That'll be 1 part per million using volume. Now this is the usual calculation that you end up doing. So mass of solute, mass of the substance that's dissolved that there's not very much of, mass of the solution, of which there'll be much more, as a fraction, and then multiply it by the part per million thing, which is 10 to the 6, which is 1 million. So doing that calculation allows you to get parts per million, when you're talking about grams in particular, because it says mass. A lot of examples of that. So I'm just going to clean the board and I'll come back with, we'll do a couple of little calculations and we'll do some conversions. See you in a moment. 3 little examples. Set the first one up already. It says 2 milligrams. Now you do need to be able to adjust milligrams, but you've got milligrams against grams, so that immediately means you can't directly do the calculation. Got to be working in the same units. You could convert that into milligrams, but the number's big, so we'll do it the other way. 2 milligrams is 2 divided by 1,000, because milli is 1,000. So 0.002 grams, because 1,000 times bigger is 2 milligrams. So 0.002 divided by 1,000 and then times 10 to the 6. Now when you do that, it comes out as 2 parts per million. There we are. So 22 grams in 5,000. So 22 grams over 5,000 multiplied by 10 to the 6. Now, if I was doing that on a calculator, what I do personally is 22 times 10 to the 6. I put that into the calculator as standard form, and then divide by the 5,000 rather than 22 to over 1,000 times. But it's up to you, it's not that difficult. And then, I don't remember the answer, I just had a quick look. Oh, there we go. And that is 4,400 ppm. So, much bigger as a concentration in ppm, this one than that one. And then finally this one's going to be in volume units. So in volume units, that means it'll be ppm v in brackets. Calculation is the same. 0.45 over 8,500 times 10 to the 6, but it will be what comes out of it will be ppm volume, and not looking for the, I think it's 53 according to my calculation there. I messed around with the numbers, I hope that's the right answer. You might want to check that, see that I've done that right. So 0.45 divided by 8,500 and then multiplied by 10 to the 6, 53 parts per million, but in volumes rather than in grams, because they're not, strictly speaking, equivalent, because obviously particles have different masses. So this would be either a solution thing, but more likely a gas in, in a contamination level of a gas within something perhaps. So there's some straightforward examples of calculating ppm. Then we're going to go on to doing, like I said, the conversions. We'll start with the percentage conversion, because it's fairly straightforward, and then we'll do the miles per decimetre cube one, which is a bit more complicated and often doesn't crop up at A level, if I'm honest. And you can tend to get the percentage conversion because it's straightforward. I just need to wipe the board. I'll see you in a moment. So the percentage concentration conversion, this is the 10,000 thing that some people remember. So the percentage will always be a smaller number than the parts per million. So when we do this one here, the percentage value will be a much smaller, it'll be 0 point something in the end. Now, in order to convert it, what you do is this: you divide by a million, which is 10 to the 6, and then multiply by 100 to get the percentage. Because percentage is just parts per 100. So kind of the same idea. So you're doing 10 to the 6 and then 10 to the 2. So 100 divided by 10 to the 6 is the equivalent of dividing by 10,000, which is 10 to the 4, because 10 to the 2 over 10 to the 6 means 10 to the 1 is 1 over 10 to the 4. So that's the divide by 10,000. So 245 parts per million divided by 10,000, 0.08123 That didn't go very well. I was going to put an extra naught in. 0.0245. I'm just going to check that that's what I meant to write. Yeah, I'll just write that a little bit clearer for you. It's my grubby rag there. It needs to go in the dishwasher, not the dishwasher. It needs to go in the washing machine. 0.0245, and that's the percentage in the air. So when you look at things like nitrogen and oxygen, they have massive percentages compared to lots of the other contaminants or low-level things. So the parts per million for oxygen and nitrogen are massive, but when you get out to some of the rarer things like xenon, the parts per million are really small, fractional in fact. So that's a fairly straightforward thing. So parts per million into percent, divide by 10,000. So percent to go to parts per million, which means you need to get a bigger number, is multiplied by 10,000. That's kind of it. Then we get on to the more difficult conversions involving moles per cubic decimeter. But I need to clean the board before we do that. See you in a minute. So here we are doing a parts per million conversion. We're going to convert moles per cubic decimeter into parts per million. So we're going to need a question. What is the chloride ion concentration in parts per million in a 0.075 moles per cubic decimeter solution of sodium chloride? Going to need how many grams of sodium chloride would go into 1 decimeter cubed of solution because of the calculation, a little step in the calculation later. Mass of sodium chloride, formula mass is 58.5. Multiplied by the 0.075, it tells you put 4.39 grams of sodium chloride into 1 decimeter cubed of water, and you would get the concentration that you'll require at 0.075. Concentration of chloride ions is 0.075 as well. That's because the formula doesn't have any numbers in it, and so the number of chloride ions released from NaCl is the same as the number of NaCl, so the concentration is the same. Sodium chloride releases 1 chloride for every sodium it releases. So that makes the mass of chloride 0.075 times 35.5. Chloride and chlorine don't have any difference in mass because the electron doesn't weigh anything to a chemist, only to a physicist. And that comes out as there is 2.66 grams of chloride ions. So you forget about the sodium because we're not asking about the sodium. In 1,000 grams of water, because of the density of water, 1,000 cubic centimetres is 1,000 grams. So, setting up the PPM calculation, 2.66 grams of chloride ions. Now, you would go, oh, it's 1,000 grams of water, but actually that's not right. It isn't 1,000 grams of water because when you add 4.39 grams of sodium chloride, it becomes 1,000 plus 4.39 grams of sodium chloride. So really the mass is 1004.39, and then 2.66 divided by 1004.39 times a million, and it comes out as 2250 parts per million. That is not the right level of accuracy for the question because there's only two significant figures in the concentration, so that is 2300 parts per million, because you round it up because of the 5. Now if you didn't do this, it would be 2260, and it would still round to 2300, and it wouldn't make any difference. The higher this concentration, the more significant it is to do this here. So if we drop the concentration to even lower concentrations, this starts to become a pointless thing to include. But you have to check. Now, we're going to do a slightly more complex example after the edit, but obviously I need to clean the board, so I'll see you in a moment. So, only slightly more complicated example, only because of the formula. So calculate the parts per million of sodium ions in a 0.0000580 moles per cubic decimetre sodium carbonate solution. You will need to know, or you kind of need to check rather than know because of the value, as it turns out, how many grams of sodium carbonate there is in the 1 decimetre cubed. And the formula mass of sodium carbonate is 106, and that's the concentration from the question, and it turns out that you have dissolved in 1 decimetre cubed 0.06148, which is not very much. And that, but you need to check just in case it's a reasonable value, I suppose, if you can't look at it and judge. The concentration of sodium ions, because of the formula, is double that. The formula contains 2 sodium ions, so the concentration of the whole substance is that, but the concentration of sodium ions is double. And therefore it's 0.00116 moles per cubic decimetre. The mass of sodium that equates to in a whole decimetre cube is, mass of sodium is 23, so therefore it's 0.02668 grams in a decimetre cubed, and that's in 1,000 grams of water. Now the setup for the ppm is that number of grams divided by the 1,000 that it's in. But actually remember it's plus the mass of the solute that goes into it, which turns out to be not a very significant contribution on top of the 1,000. So it's 1,000.06148, which in terms of the accuracy of the answer, it doesn't make a difference. And it comes out as 26.7 parts per million. Doing it without that would also give you 26.7 parts per million. So sometimes it's kind of not worth it. But you do have to check, because if the concentration is, well, the more significant in size the concentration, so the larger the concentration, the more that this value starts to make a difference. So we'll go on to do some more. But we'll have to have a little edit whilst I clean the board. So here we are with a relatively similar calculation because of the formula. What is the concentration of bromide ions in parts per million for a solution of that small amount, 0.00815 grams of magnesium bromide in 220 cubic centimetres of water? Now there are a couple of ways to get to this value here, the mass of bromide ions that you've dissolved. I go this method because this is the way my other wall has done it, but you could do it as what part of the magnesium bromide is. You know, bromide ions, 2 lots of 79.9 over the formula mass, but doesn't save much time. So, formula mass is 183.8, 24 and 2 lots of 79.9. So therefore the moles of the actual substance, the magnesium bromide, the whole substance, that the mass divided by the formula mass, there it is, 4.4342 times 10 to the minus 5 moles. Moles of bromide is, because of the formula, double that. So there it is, doubled, 8.868 times 10 to the minus 5. And then, how much mass does that equate to? And you multiply it by the atomic mass of bromine, because it's a bromide ion, doesn't make any difference because the electron doesn't weigh anything in chemistry terms. And there's the mass of bromide ions that you get out of that. So that is dissolved in that. Remember, you've got to add in the mass of the solute onto the solvent. The solvent is now not 1,000, because that was one of the changes, is what happens when you don't do moles per cubic decimetre, but you have a mass in some other different volume. And so here, there's the mass of bromide ions in grams. There's the mass of the water and the mass of the solute, the 815 with the 2 noughts in front. Multiply it by a million, and the answer comes out as 32.2. This makes no difference to this answer at this level of accuracy. 3 significant figures, because that is, I suppose you could say that was 2, and it would be 32 parts per million. I assume that that was 3 significant figures. No evidence for that, but anyway, it's about the method. So there we are, and I'll just do one more, and then we'll do a couple of other things and we're done. See you in a moment. So here we are with something slightly different, because it's now parts per million in a volume, so ppm with V in brackets, or without the brackets. What is the parts per million in volume of the air if 6.8 cubic centimetres of hydrogen sulfide is released into a room that has a volume of 26.5 metre cubed? It's probably not a laboratory sized room, that's more like a household room. So 6.8 cubic centimetres in 26.5 metres cubed is what we're saying. Now there are, as we said earlier, 1 million cubic centimetres in a metre cubed. That's because a metre is 100 by 100 by 100. That's 10 to, that's 100, that's 10 to the 6. So 6.8 cubic centimetres in 26.5 times 10 to the 6 centimetre cubed, that means, because those statements are the same. Now 6.8 cubic centimetres in 26.5 million cubic centimetres is not parts per million, because parts per million will be for 1 times 10 to the 6. So therefore that volume is in 26.5 times the volume it needs to be in for ppm value. So you just divide by the 26.5 and scale the 6.8 down by 26.5, and the answer comes out as 0.257 parts per million volume. Done. See you in a moment. So this time, slight variation. It's a mass of substance, and this is quite a horrendous moment, because that's quite a lot of bromine, 2.55 grams. Escapes into a laboratory of 56 metre cubed. So it's going to happen at room temperature and pressure, because that way we can do a simple calculation. Don't get involved in PV equals nRT. So 2.55 grams of bromine is 0.01596, because the formula mass of bromine is 2 lots of 79.9. 1 mole of gas at room temperature and pressure, 24,000 centimetre cubed. That's an approximation, but it's pretty good. Volume of bromine therefore escaping, because it escaped as a gas, 24,000 times the number of moles, and it's 383 centimetre cubed. That's quite a lot of bromine vapour, even in a reasonable sized laboratory like 56 metre cubed. That's going to result in everybody out and all that kind of stuff. So 3.83 divided by 56. Why have I done that? 383 is in 56 metre cubed. 56 metre cubed is 56 million cubic centimetres. So 56 times 10 to the 6, and 10 to the 6 is the ppm thing. So all you've got to do is scale it down from 56 metre cubed to 1, because that's 1 million. So 383 divided by 56, and the answer comes out as 6.8 parts per million, but it's done in volume rather than in mass, because you can't do the mass of 56 metre cubed of air, because, well, you could, but it's air, you know, it's not one substance. So there it is. Can do a little bit more at the end, and then we're done. There should be some accompanying questions if you download them and have a practice, if you want to practice exchanging this, and I know people ask for that. I'll see you in a moment. So the last bit is just a summary of the 2 directions of transferring between one form and another. Parts per million into standard moles per cubic decimetre, and then moles per cubic decimetre into parts per million. Not going to do it with an actual example, they'll be in the accompanying questions. So, converting parts per million, first of all, into grams per cubic decimetre. So, parts per million is grams in a million. So you want to go for grams in 1,000, So you divide it by 1,000 because a million to 1,000 is divided by 1,000. That's parts per million divided by 1,000. That's then grams per cubic decimetre. You then want to convert that into the number of moles that there is in that 1 decimetre cubed, because that's how you do standard concentration. So you divide by the MR of whatever it is you're referring to. And that then gives you the moles per cubic decimetre as a standard sort of concentration for chemistry. This will be the reverse of that process. The 1,000 is in there, the MR concentration and grams per all in there. It's just the reverse process. So you start with moles per cubic decimetre, you start with the standard concentration. So moles per cubic decimetre, first thing to do is to convert it into grams per cubic decimetre. So if you know how many moles and you know the MR, you multiply the two together. That gives you the number of grams in a decimetre cubed. You then need to scale your decimetre cubed up to a metre cubed, which is 1,000 times the size. So the whole thing becomes how many grams, not in 1 decimetre cube, which is about so big, but in 1,000 of those. So you scale it up by 1,000, and out of that comes the parts per million. There we go. So they are the reverse of each other. There'll be some examples about that. That's kind of it. Talking more generally about concentration, luckily almost all of chemistry talks about moles per cubic decimetre. This parts per million thing, I almost wish it wasn't there because it is just a confusion for people. But ideally, if you review this video, maybe go back over it, make some notes, look at the examples, write them out, do them yourself, check that you got the right answers. Might spend a bit of time getting to grips with parts per million. It's all about scale. And then have some practice on the practice questions, which will have the answers as well. And then maybe you'll be alright. Talking, like I said, more generally about concentration, if you really need much more practice about concentration, I have a book. I published a book about concentration at A level, and it's much more than just how do you work out concentration. It's got all sorts of facets of concentration in, and how it influences various other parts of chemistry. So, yeah, available from Amazon. Reasonable price of £7.99. Lots of practice questions in there with the answers fully explained, not just here's the answer, but how on earth do you get that answer. If you want more practice generically about concentration, that's the place to go. Thank you very much. I no doubt will see you again very soon for something else. But other than that, and I know this has been quite long, but thank you for staying with me. Bye bye.